All right. Hello again, everyone. My name's Jack, and I'm presenting Ice Shelf Calving, a graph theoretic approach with quantum computing. In this project, we looked at how we could model ice shelves and the fractures that form inside them. My mentors were Cheryl and David. So first of all, why we think it's important to look at ice shelf calving. This is because ice shelf calving and blocks of ice falling into the ocean is a dominant contributor to sea level rises. And these fracture networks can determine whether there'll be catastrophic failure, meaning that blocks of ice completely separate and fall into the ocean. And an example of this is the Thwaites Glacier, also known as the Doomsday Glacier, which could raise sea levels by 2 feet or more if it falls into the ocean. So, all right, so why ice shelf fractures are difficult? This is because the fractures can evolve and branch out and interact with each other, even if they're not connected. And this means, this makes it difficult to predict what could happen next. And additionally, classical methods of modeling these systems use finite element modeling. And to analyze with great detail and accuracy of these crack interfaces, you need to make the meshing finer and finer, which requires higher and higher computational cost. So to talk about the scope of this project, we're targeting the mesoscale, which we define as where the fractures are forming, and we want to model those using graphs, generate Hamiltonians, and do an optimization to see how these fractures evolve. And to inform this, we look at the local crack physics, mainly the crack tips and the stress fields around them. All right, just a quick check. Should be all right. Yes. All right, I'm just going to keep going from now. So how does quantum fit into this? So quantum, we think, would be advantageous over classical methods because of some of the challenges of modeling these systems, which include fracture growth, and the characteristics include sort of competing paths of how the cracks evolve. So some are more favorable than others, and sometimes these cracks can grow at the same time, which makes it a big combinatorial problem. This is our modeling pipeline, and we start with the fracture physics, and we generate an energy-based scoring from that. And then we look at an ice shelf as an input that has fractures in them and turn that into a weighted graph. From that, we do some classical failure analysis using MidCut and also fracture evolution via MaxCut QAOA, which is the quantum application here. To touch on the Hamiltonian fracture mechanics, so this is the formalism that we did for the physics-based scoring system. And we looked at this as a way to map things onto our graph. And the advantage of this formulation is that it converts higher order PDEs into first order equations. And it's an especially powerful tool when we're looking at anisotropic and mixed mode loading, which you take into consideration when you've got asymmetries in direction and whatnot. And it's also pretty cool to use this formalism because Hamiltonians are used a lot in quantum. And although this is a classical regime, using similar maths to make problems more efficient is pretty neat. So in this project, we looked at these as a way to sort of get a sense of how the fractures evolve and what frameworks we could use to do the fracture-based scoring. And we've kept this to be used at a later time when we look at anisotropic modeling. So for our pipeline, we start with a square lattice representing a volume of ice. And these nodes represent material regions, so little blocks of ice. And the edges on this graph are the bonds that connect these different volumes of ice. We also place edge weights on these based on the release energy, which we'll look at in the QAOA part. And there's also a periodic boundary condition. So it's actually a looped sort of cylinder, if you like. And this simulates an infinitely long plane, meaning we can get rid of any edge effects of the lattice. And from this lattice, we can take the dual graph, which allows us to look, from which we look at the fractures themselves. And this conversion is something that's extensible to any planar geometry, including some 3D cases. And the reason we chose a square lattice is firstly because it's very simple and easy to interpret, and constructing the dual graph from it is very easy. But it also matches the architecture of the new Nighthawk processor and the upcoming IBM hardware, which means there's potential for more efficient embedding without losing any information. So to touch on the min-cut static failure analysis, we basically use this as a way to see how close the ice shelf is from splitting into two, and then you can imagine how it falls into into the ocean. And now the most important max cut QAOA part. We apply this by in the sense that we implement this for breaking K bonds per step, K being greater than 1, and optimizing for maximum energy release. And we also add a constraint so that add a penalty so that the fractures that it chooses are all connected. And this Cardinelli constraint, the K bonds per step portion, allows us to look at sort of time discretized evolution, which is pretty good for predicting different steps, and we can see how well our model is predicting things. So here's a bunch of steps that we went through comparing a greedy method versus a QAOA method. And although this is an air simulator, we can see how the QAOA version can capture some richer physics in more complicated systems. And yeah, so some key takeaways from this project is that the graph abstraction, graph formulation of the ice shelf is working pretty well so far, and we think we can extend it to more complicated cases. Using the min cut and max cut hand in hand to look at the failure and the growth of cracks is also pretty useful. And finally, the pipeline that we've designed itself is very modular, so we can switch out the optimization layer, we can switch out some of the physical models to increase the physical realism of the modeling itself. Here's a list of all the future work we hope to do. And if anyone's curious or would like to work with us in the future, please, reach out. Thank you.
Great. Thank you so much. That was a great presentation.
All right.
I'm glad that we got to see it.
Hopefully that was all good.
Yes, all good.